Here we have some copper 2 sulfate. It's actually hydrated. When copper 2 sulfate is hydrated, we have this nice pretty blue color. When it's not, when it's anhydrous, it's kind of a whitish gray color. See my next video for a bit on that. But anyway, this is hydrated copper 2 sulfate. We're going to use this to make a fairly saturated solution. Saturated meaning we will have dissolved as much of the salt as we can dissolve at that certain temperature that's saturated. If you could still dissolve more, if you put more in and stirred it and it dissolved, then your solution was unsaturated. We want a fairly saturated solution. So we're going to dissolve some of this. How much do we need to dissolve? Well, we need to know the solubility, i.e. how much can dissolve at whatever temperature per whatever volume we have. So I want the solubility of copper 2 sulfate in water. I do a quick Google search and I come up with something like this. Now, this is straight from Wikipedia. Unfortunately, it doesn't tell me this many grams per 100 mils or anything like that. What it does tell me is a nice little room temperature, sweet, so I'm going to be using that. But it also tells me 1.26 molar. Now, what the heck is that? Well, that is a way of measuring the concentration. We call it molality. It's very similar to molarity. Molality is how many moles do you have dissolved per kilogram of solvent, and in this case our solvent is going to be water, as opposed to the more common molarity, which is how much of the salt you have dissolved per liter of solution. Okay, so we talk about things like moles per liter is a good way to talk about the molarity. In this case, we have the molality. It's a bit similar, but also a bit different. So let's start with this one. We'll do this. Molality, actually symbol, sorry, I'm used to using moles. Molality is the symbol M, and that is given by the number of moles divided by the kilograms of solvent. Okay, so we're going to have 100 mils. Well, we'll work out the solubility in 100 mils. We'll actually have a bit less than that. I'm going to use 75 mils, which I'll explain in a sec. But we're going to work out the solubility per 100 mils. So we've got 0.1 of a kilogram. So what we have is actually 1.26 times 0.1. I'm just rearranging this to find the number of moles. Okay, and that's of course going to be 0.126 moles of the copper 2 sulfate. Now, moles is the SI unit for how much of a substance do you have. Okay, so SI unit, the standard international system of units. Okay, so System International de Unité, right? SI units. Like for distance, the SI unit is the meter. For time, the SI unit is the second. Okay, for amount of a substance, the SI unit is the mole. And the symbol for mole is mol. Okay, so there we go. That's how many moles we have, 0.126. We need to convert that into a mass. Okay, so we have another equation that the number of moles is equal to the mass divided by the relative mass. So we rearrange this one to find the mass. It's equal to moles times the relative mass. Well, moles were just worked out at 0.126. But now we need to work on relative mass. So we look up our trusty periodic table, and this is what we find, something like this. We're going to be using copper, and here's its relative mass. We're going to be using sulfur, and here's its relative mass. We're going to be using 4 oxygens, and that's the relative mass of each one. So the relative mass of the copper 2 sulfate, we're just going to add up all of these masses together. Now, you'll note actually another bit on the side, I'm calling it copper 2 sulfate. I'm not just saying copper sulfate. There are actually 2 copper sulfates. There's the one that we are using, and there's this one. Now, the one that we're using is called copper 2 sulfate, and the one that we're not using is called copper 1 sulfate. Technically, they're both copper sulfate, but they have very different properties. They're actually different compounds, so we kind of need to be specific. This is called, the one we're not using, is called copper 1 sulfate because it was made from the copper 1 ion. Okay, sulfate ion is SO4 2-, but of course, compounds don't have charges, so I would need another copper 1+ ion to cancel out all those 2 negative charges. So when we write the formula, this is saying actually I've got 2 of these for every sulfate I've got. So we need two of them, but it was made from the copper 1 ion, Cu1 plus. So we call that copper 1 sulfate. What we actually have is copper 2 sulfate. It was made from the Cu2 plus ion, the copper 2 ion. And when we hook that up with the sulfate, all the charges cancel out nicely. And we just need one of the copper ion and one sulfate ion. So there we go. We only need one of them, but it came from the Cu2 plus ion, which is why we call it copper 2 sulfate. And in writing that, we put the 2 into the name, into the first word. We put copper and then Roman numerals 2, and then next word sulfate. So there we go. That's why I'm saying copper 2 sulfate, not just copper sulfate. Okay, cool. Back to that relative mass. We have the relative mass of our copper 2 sulfate is equal to, now we've got 4 times 15.994 because we've got 4 oxygens. We've got plus 32 and a little bit. We've got plus 63 and a half-ish. Now that's going to come out at 159.6086. Now, I just know that one. I wouldn't recommend going out and memorizing stuff like this. That would just be silly. You just look it up and work it out and when you need it. But because I've used copper sulfate, well, a little bit over the years, I've just gotten used to its relative mass. Okay, so we can now put that into our equation, number of moles times the relative mass, to work out our mass of the salt. So we'd times that by 159.6086. Let's do that. 0.126 times 159.6. Sorry, just tapping this out on my calculator / phone / calculator. That comes out as a mass of 20-ish, 20.1-ish. So what we can do is we can say grams. Now that is to 1 decimal place. Now in terms of this prac, I'm not really too concerned about being super accurate, but I'm just wanting to show you the proper method of working it out. Okay, so we'd work out it, we'd get our answer, we'd put the units, but then we'd show, have we rounded it? Well, yes, I have, because my calculator doesn't say 20.1 exactly. But I'm just going to call that 20-ish anyway. So that is the solubility of copper 2 sulfate in water at 20 degrees is just over 20 grams. Okay, now that's per 100 grams of this solvent, right? So per 100 mils, essentially. 100 mils has a mass of 100 grams. So I'm not actually going to use 100 mils, I'm going to use 75 mils. Okay, now the reason I'm going to do this is simply because if I'd used 100 mils, I'm actually going to divvy it up into 3 test tubes, this solution, and if I'd used 100 mils, I'm just going to have some stuff left over, which is no real biggie. No harm, no foul, but I would use more salt. I'm just trying to conserve my salt. We try and conserve chemicals where we can, okay? Because I'm not actually going to measure out 20 grams. That's how much could dissolve at 20 degrees Celsius. I'm actually going to heat this up. I'm going to get it boiling. Okay, so we actually need the solubility also at 100 degrees Celsius. So let's go and look that one up. And here we go, another search. It wasn't on Wikipedia, the solubility at 100 degrees. So I continued my search and came up with this. So here we go. Here's the solubility of copper 2 sulfate in 100 mils of water at 100 degrees Celsius. I said mils, this says cc. That's cubic centimeters, but 1 cubic centimeter is equal to 1 milliliter. So if you see cc, it's the same as mils, right? So this says if I heat it up and get it boiling, or if it were at 100 degrees Celsius, I could dissolve 75 and a half-ish grams of the salt if I'd had 100 mils to dissolve it in. Now, when I heat this up, the temperature is not going to be exactly 100 degrees. I'm in Canberra. I'm not at sea level. Remember, water boils at 100 degrees Celsius, yes, but only if it's pure water, and that's at 1 atmosphere of pressure, so 101.325 kilopascals. Usually we just say at sea level because if you were at the beach, you would have 1 entire atmosphere weighing down on you, so that would be your pressure, that 1 atmosphere of pressure. I'm in Canberra, I'm not at sea level, so the pressure is less. There's less than an entire atmosphere pushing down, so the water in camera boils at roughly 98.5-ish, maybe 99 degrees Celsius. And also remember that that whole 100 degrees Celsius at sea level, but that's pure water. This water is not going to be pure. I'm dissolving some copper-2 sulfate in it, so that will also affect the temperature. The boiling point. So you can see I'm really not being too accurate here. Like, I tried to show you the math. I tried to show you, show your rounding, like do the right method, yes, but I don't really care too much for this prac. I just want sort of rough-ish. Now, so 75-ish grams will dissolve at 100 degrees Celsius in 100 mils of water. I'm not going to have 100 mils. I'm going to have 75 mils, mentioned just earlier, simply for the sake of, rather than weighing out 75 grams, could I use less of the salt? And yes, I can. So I'll take my 75.4. Now that's per 100 mils, so I'll take 3/4 of that, so I'll times that by 0.75, and I come out at 56.5-ish grams. Okay, so my solubility of copper-2 sulfate in water at 100 degrees Celsius is 56.5-ish grams per 75 mils. Okay, now when we compare that with 20 degrees, so this is at 100 degrees Celsius. At 20 degrees Celsius, it was about 20-ish, it was about 20.1-ish grams per 70. Oh, no, that was per 100 grams. Okay, I've only got 75 mils, so I'll take 3/4 of that. We'll get rid of that, and we'll call it 15-ish. So 15-ish grams per 75 mils at 20 degrees. Now, the reason why I worked out the solubility at both temperatures, like I'm going to get it boiling, so I could have just worked out the at 100 degrees, but I just wanted to check that the solubility at 20 degrees wasn't so great that I won't actually have much salt dropping out. See, what's going to happen is I heat it up so I can dissolve this much salt, but then I'm going to leave it at, and it will cool down to room temperature. Now, when it cools down, say to 20 degrees, only 15 grams can be dissolved, not 56 grams. So 41 grams will actually have to come out of the solution. It will drop out of solution and start forming, form as a solid, so start forming the crystals. So 40-ish grams I've got that will be building up my crystals. So that's a good amount. Like if I'd check the solubility at 20 degrees and at 100 degrees at 75, at 20 degrees at 73, well, that's very little of the salt that is actually going to drop out. So I'm not going to get much crystal formation. However, I can see now that about 41 grams will drop out of solution, so I can get some decent crystal formation. So let's stop talking and stop doing math, and let's go and do the prac now. So first we turn the balance on. We're going to need something to measure the copper-2 sulfate into. And once we've put this on the balance, we actually zero it. We don't want to include the mass of the little paper cup, just the copper-2 sulfate. So we're actually going to be getting quite a bit of that. See, that much is only 8.5 grams. We want 56 grams of copper-2 sulfate. So we're going to be putting quite a bit into this cupcake holder. Whether you call this a patty pan in Australia, I've heard people call it patty pan. But there we go, roughly 56. So 56.2ish, 0.25, we want roughly 56 grams. So there we go, it's roughly 56 grams. So we're good to go with that. Now we're going to dissolve this in some water. Right, so we have some water to dissolve the copper-2 sulfate. We don't just have some water, we actually have 75 mils of water. The solubility of copper-2 sulfate is about 20 grams per 100 mils, but that's at 20 degrees Celsius. Now, we want to get this water boiling. We're going to make a nice hot saturated solution, so we can cool it down and have some of the solid form. We want to form some crystals. So if I had 100 mils of water, I could dissolve 20 grams of copper sulfate. Well, I've just put in 56 grams and I don't actually have 100 mils of water. This is not all going to dissolve. All right, 20 grams of this will dissolve if I'd had 100 mils, so a bit less than 20 grams. In fact, what about 15 grams since I've only got 75 mils. But what I'll do is I'll actually heat this up. Let's get a Bunsen going and we'll heat it up, because when you heat a solution, you can dissolve more salt. So let's just fire up this Bunsen. Just had to put the my phone down for a sec so I could light that, because I've only got two hands. And remember, it's a one-person job to fire up a Bunsen, but you do need two hands. I've got an entire video on how to fire up a Bunsen. Turn to the heating flame by turning the collar, which opens up the air hole to give us this nice blue heating flame. So we will heat this solution, and I'll go get a stirring rod so we can stir it around and help the copper sulfate dissolve. Okay, so that's heating up nicely. We'll give it a bit of a stir. Now, so I did the math, and at 100 degrees Celsius, 75 mils of water will dissolve about 56 grams of copper sulfate. That's why I weighed that much out. It's about 56 and a quarter from memory. I actually, when I put this whole video together, I will show you how the math is done. We can actually hit a number of different science aspects with this prac. So we'll just leave that heating. And whilst that's going, I'll set up an ice bath. Okay, so I want an ice bath, so I'm going to have to start with some ice and then do a bit of this to it. Because I don't want massive big chunks of ice in my beaker. To make an ice bath, we really want crushed ice. So with this, I can now make an ice bath. Just reach over here, get myself a beaker, and we'll scoop this ice into it and then add some water. There's our instant ice bath. Let's just break you up a bit. Wait, come back. Better. Okay, so the solution is nicely boiling away now, and we can see the solid copper sulfate has in fact dissolved. So that's grand. We can turn the Bunsen off. We've now got a solution of copper sulfate. It's nearly 100 degrees. It's not quite. In camera, of course, we're not at sea level, so water boils in camera at about 98.5 degrees. And this is, of course, not pure water. We've got some impurities in there. We threw a whole lot of copper sulfate, so that will affect the boiling point as well. But it's about 98, maybe 99 degrees. So nice and hot, and we can see quite clearly that all of the copper sulfate has, in fact, dissolved. So that solution is fairly saturated. At 100 degrees, we can dissolve about 75 grams of copper sulfate, so that's per 100 mils. I've got 75 mils, so I should be able to dissolve about 56 grams, and sure enough, I did. So it's a pretty saturated solution. So here's with the crushed ice. We add some water, and we have instant ice bath. There we go. One ice bath to sit a test tube into. Now, that beaker of copper sulfate has just been boiled. It's very hot. I don't want to touch it with my fingers because lab rule 101, hot glass looks like cold glass. You think, oh, there's some glass, I'll pick it up, burn yourself, you break it, not so good. So I have this massive big glove here, so I can actually just
pick it up. What I want to do is divvy up this copper 2 sulfate solution into 3 test tubes. Now, one of these test tubes will be going into an ice water bath. Is that on? Yep, that's on screen. Another one will sit just in a beaker, and another one in a beaker of cotton wool for insulation. So let's just divvy up this copper 2 sulfate first. We'll put some into here. Throw that in the ice bath. Throw meaning place nicely. Some more of the same solution into a different test tube. And the third test tube, which will be surrounded by cotton wool for insulation. Get rid of the glove now. Now, too much solution in there. Some of that's not actually insulated, so we have a lot less in the ice bath, so we can transfer some to this one. There we go. That should do us. Alright, so what we have now is 3 beakers, each with a test tube of our copper sulfate solution, nice and hot. That will of course cool down. They will all get to the same temperature, room temperature, eventually. But we're going to cool them down at different rates. We've got one test tube in an ice bath, so that'll cool down nice and quickly. Another test tube just sitting in a nothing bath, just in a beaker, so that'll be our medium cooling down. And then we have cotton wool surrounding this third test tube. Now the cotton wool is going to act as an insulator. So this will cool down to the same temperature, down to room temp, but it will take longer to get there. So that's our setup for this prac, and then we have to leave it for about a day or so for crystals to actually form, and then we can compare the size of the crystals. So there we go. We're just going to leave this here. I wrote overnight on the sheet. It might take a day or two actually, but I'll check it tomorrow, and we'll see what's going on in terms of crystals. Not just whether or not crystals are growing, they will as the temperature cools down. We've got too much salt dissolved, so some of it will have to come out of solution and form a solid again. But remember, what we're really looking at is the size of the crystals.
And here we are again. So it's the morning of the next day. I didn't actually need to leave it for more than a day. In fact, less than a day apparently was sufficient from yesterday afternoon after school until this morning. So if we look carefully now, if we look in this ice bath at the moment, actually it's not an ice bath anymore, is it? It's a water bath because the ice is all melted. But if you look carefully, you can see some crystals, ditto in the middle test tube there. We can see some crystals at the bottom. Can't quite see anything in the insulated test tube because we can't see through the cotton wool. But that's fine because we're going to pull out the test tubes and have a look at them. So let's start with the test tube from the ice bath. And voila, we have some crystals of copper 2 sulfate have formed. Remember, it was fairly saturated solution. So as the solution cooled down to room temperature, in this case pretty quickly because it was in the ice bath, then some of the copper 2 sulfate came out of solution and started to form a solid. So we started to grow some crystals. So we can see crystals quite at a good amount of crystals, but they are fairly small. So we've got little crystals, little crystals. Lots of little crystals have formed throughout. Okay, so definitely formed. Yay, grand. We knew they were going to form. It's the size that we're really looking at, and what we're looking at is small crystals here. So now the middle test tube, which was just sitting in a beaker, it wasn't insulated, but it wasn't cooled down particularly quickly either. Crystals definitely larger than what we just saw. So in the ice bath, really small crystals. Without the ice bath, just normal cooling down, we have larger crystals. Now, if we take the one out of the cotton wool, if we have a look at that test tube, we see even larger crystals. I mean, look at the size of this guy. It's huge. There's another large one behind him, another large one at the back there. So we have really good sized crystals now, much larger. Might actually be easier to see without the copper 2 sulfate solution. So don't worry, I tipped it out. And here we go. So this is the test tube that was cooled down quickly. in the ice bath. And again, we can see the crystals quite nicely, but they are fairly small in size. The medium cooling rate, let's call it that, test tube, the middle test tube, has some larger crystals, definitely larger than what we just saw. But the test tube that was wrapped up in the cotton wool, or surrounded by cotton wool for insulation, has the largest crystals. We have a really good sized crystal here. Nice one here, sort of, it would come down there, it's 3D. We've got a big one down here. So we have some large crystals going on there. Cool. Now, this is a photo of granite. Now, granite is a type of igneous rock meaning coming out of a volcano. This is plutonic igneous rock. And what happened to form this is the magma inside the Earth was cooled down fairly slowly. And that allowed time for the crystals to grow a decent size, similar to what we saw in the prac. If the magma had come out the top of the volcano, and now we change its name, we call it lava, and it suddenly met the relatively cool surrounding air temperature, that magma would cool down rapidly and the crystals would be much smaller, like we see in obsidian. Now, obsidian is lava that is cooled down rapidly, so rapidly, in fact, that we can't actually see any crystals. If we go back to the granite, very, very obvious crystals here. We've got all this black stuff, all this white stuff, we've got all this pink stuff, very obvious crystal structure. The pink is feldspar, the dark brown or black is from mica, and the quartz is the sort of clearish pinky or white crystals. So we've got different minerals in there, but we can definitely see the different crystal structure there, different grains of crystals. And the obsidian, the crystal grains are so small that we can't actually see them. It just looks nice, solid, shiny black. Okay, shiny because it has high luster. Right? It's very lustrous. It reflects the light very well. So what's going on here in terms of, remember, it all comes down to how fast it cools down and hardens into this rock. Okay, so in terms of the prac, we were looking at how quickly the copper 2 sulfate solution, that saturated solution, cools down, and then the salt has to come out of solution. In terms of the rocks, like the granite and the obsidian, what we have is from the magma chamber, we could actually have some magma. Remember, on the inside of the Earth, it's called magma. When it comes out, we call it lava. So inside magma, outside lava. So what actually could happen is that maybe it may not actually come out of the volcano. It might just sort of move off to the side, away from where all this high heat area is. So if it moves off to the side, it's not going to be as hot. So it will start cooling down. However, it's still in the earth, and the deeper you go, the hotter it is. So it's still in the earth. There's still some heat there. So it's a bit cooler than the temperature of the magma chamber, but it's not all that much cooler. So it will cool down, but relatively slowly. And so that gives us the granite that we saw with the very obvious size of the crystals. And so this is igneous rock. Igneous rock is basically lava that's cooled down, or magma that's cooled down and hardened into what we think of as normal hard solid rock rather than plasticized rock. So this is all igneous rock. So igneous, the word igneous is one of the rock types. Igneous actually comes from the original Latin ignis, meaning fire. So the Latin ignis, meaning fire, is where we get this igneous type of rock. But when it cools down and slowly, and so it's still in the Earth's, within the Earth's surface, or under the Earth's surface, we call this plutonic. So this is plutonic igneous rock. Now this, when it comes out the top, then we change its name. So this lava now comes out and flows down the side. We have a little lava flow. This lava meets the cool surrounding air temperature and cools down much more quickly. And so when this hardens, we get the rock with the much smaller crystal grain sizes. So small, like in the obsidian, that we couldn't actually see them. And this is another type of igneous rock, but this we call volcanic. So we've got volcanic igneous rock, and we have plutonic igneous rock. They actually have other names as well. Remember, this plutonic rock, it's still inside the planet, isn't it? It's inside the structure of the Earth, so we call it intrusive. So plutonic igneous rock is also, oh, wait, I don't see, I don't want to see, is also called intrusive igneous rock. And volcanic igneous rock, well, it's outside. So surprise, surprise, X meaning out. So this is extrusive igneous rock. So our two rock types there, we had obsidian, that is extrusive igneous rock or volcanic rock. Can't see the crystals because it cooled down very quickly, so the crystals are so small we can't even see them, even with a magnifying glass. And then we have the granite. We would have it clean if I got rid of all these red marks. We have the granite there where we can see the crystals because the crystals are much larger in size because it cooled down much more slowly. So this is an example of plutonic rock or intrusive igneous rock. So there we go. Our prac was really related to the different rock types and the minerals, the crystals that you can see in the rocks. So I was just sort of working with some earth science with my students. So that prac is really related to seeing or not being able to see the size of the crystals in different rock types.